Quantum computers leverage quantum bits, or qubits, which can exist in multiple states simultaneously, unlike classical bits. This enables them to solve complex problems exponentially faster. Key technologies include superconducting circuits and trapped ions. Challenges involve error rates and qubit coherence. Future developments aim to enhance scalability and error correction, revolutionizing fields like cryptography and quantum computing. Hardware is pivotal in advancing computational capabilities. It encompasses technologies like superconducting qubits, trapped ions, and topological qubits. Each technology presents unique challenges such as error rates and scalability. The outlook is promising, with ongoing research aiming to enhance stability and performance. Future developments focus on achieving fault tolerance and practical applications across various industries. Quantum computing hardware includes three main types: analog quantum computers, noisy intermediate scale quantum computers, and fault-tolerant quantum computers. Analog systems lack abstraction layers. Noisy intermediate scale quantum systems use one-layer gates, and fault-tolerant systems employ two layers, quantum error correction to gates. Each type offers unique capabilities and challenges. Quantum computing leverages the quantum states of subatomic particles, using qubits instead of classical bits. Qubits exhibit superposition, existing as both 0 and 1 simultaneously, and entanglement, where the state of one qubit affects another. These properties enable quantum computers to perform numerous calculations at once, though measurement collapses qubits to classical states, erasing quantum information. Quantum computing offers transformative potential by exceeding classical limits in optimization and simulation tasks. It addresses complex scientific problems impractical for classical solutions due to time or memory constraints. This revolutionary power can impact fields like pharmacy, energy, and logistics, leveraging a fundamentally different technology rooted in advanced scientific principles. Key metrics for quantum scalability include coherence time, gate latency, gate fidelity, and qubit mobility. Longer coherence times and lower gate latency enhance performance, while high gate fidelity ensures accuracy. Common misconceptions include equating more qubits with better performance and assuming all universal quantum computers are inherently useful. Effective computation time and error rates are crucial considerations. Analog quantum computers evolve real-world quantum systems over time, excelling in quantum simulation and optimization. They efficiently utilize hardware resources and operate rapidly without abstraction layers. However, they are highly specialized with limited Hamiltonian options, and hardware noise can be a constraint. Often called quantum simulators, they focus on simulating specific physical phenomena. NISQ gate-based computation involves using imperfect quantum gates for noisy universal quantum computation, often with arbitrary rotation gates. It's ideal for quantum simulation of closed systems, variational quantum algorithms like VQE for chemistry, and potentially quantum machine learning. While flexible and fast, hardware noise and qubit coherence time limitations pose challenges. Fault-tolerant gate-based computation, FTQC, uses quantum error-corrected gates for perfect universal quantum computation, ideal for high-accuracy simulations and factoring. It offers reliability and surpasses qubit coherence limits. However, it demands numerous physical qubits and gates and is slow due to quantum error correction overheads. FTQC is the ultimate, yet challenging quantum computing goal. Analog quantum computers excel in evolving real-world quantum systems with efficient hardware use but are limited by hardware noise. Noisy intermediate-scale quantum, NISQ, gate-based models offer flexible, fast computation but struggle with noise and coherence limits. Fault-tolerant quantum computing, FTQC, provides reliable, error-corrected computation, ideal for high-accuracy tasks, yet demands extensive qubits and gates, making it slow due to quantum error correction, QEC overheads. The current quantum computing landscape features noisy analog and noisy gate-based systems, with fault-tolerant gate-based systems on the horizon. Unlike classical computing, there's no single transistor for quantum computing yet. Large tech companies and startups are racing to develop scalable quantum computers, driven by significant government funding due to their potential impact on national security. Quantum computation relies on superposition and entanglement. The DiVincenzo criteria outline essential requirements: robust quantum information representation, universal unitary transformations, fiducial initial state preparation, and output measurement. Scalability is crucial. Small quantum computers lack practical utility. These criteria guide the development of viable quantum technologies, ensuring they can store, manipulate, and measure quantum information effectively. Superconducting circuits utilize Josephson junctions, operating at millikelvin temperatures. They offer fast operations and compatibility with existing fabrication techniques. Despite their maturity and backing by international business machines, Google and Intel, challenges include limited coherence and susceptibility to quantum noise. These circuits require near absolute zero temperatures, posing scalability issues due to size and error rates. Trapped ions utilize individual atoms in a vacuum, controlled by electromagnetic traps and laser pulses. They offer long coherence times, precise quantum gates, and high connectivity, making them a mature technology. However, challenges include the complexity of full-stack software development, as seen with IonQ's architecture. Neutral atoms, unlike trapped ions, use uncharged atoms held by lasers. They promise large scalability and can operate at room temperature. However, entangling qubits at a large scale remains challenging. Key players include Quira, Pascal, Quantinuum, Rigetti, Atom Computing, and IonQ. Photonic qubits encode information in photons, leveraging silicon infrastructure. Challenges include difficulty in performing gates, lack of single photon sources, and photon loss. Kerr media issues and scalability also pose hurdles. Leading players include Xanadu, PsiQuantum, Orca Computing, and Tundra Systems Global. Spin qubits leverage electron or nuclear spins in quantum dots or nitrogen vacancy centers in diamond. They offer a small footprint, high density, and compatibility with complementary metal oxide semiconductor technology. However, challenges include decoherence from electrostatic fluctuations, precision fabrication needs, and slower nuclear spin operations. Key players include Intel, Delft, and CEA-Levy. Topological qubits leverage non-abelian anyons, like Majorana zero modes, for quantum computing. They offer hardware-level error resistance and theoretically long coherence times due to stable topology. However, they remain largely theoretical, challenging to engineer, and less mature. Microsoft and Nokia Bell Labs are key players in this promising yet nascent field. Nuclear magnetic resonance uses nuclear spins of atoms, mature for small-scale experiments but limited in scalability. Molecular magnets show potential but face practical challenges. Quantum dots, constructed in semiconductors, promise scalability but struggle with decoherence. Silicon spin qubits highlight potential within silicon. Nitrogen vacancy centers in diamond, activated by laser, measure fluorescence, yet face industrialization challenges. Quantum dot. Technology Initiative and Commissariat à l'Énergie Atomique are key players. Superconducting circuits offer fast speeds and high scalability, but suffer from medium noise and sparse connectivity. Trapped ions provide low noise and high connectivity, yet are slow and limited in scale. Neutral atoms balance scale and noise but have sparse connectivity. Coherence controllability trade-offs impact performance, with longer coherence times increasing latency. Mobile qubits in ion traps and photon-based systems enhance entanglement and communication, crucial for long-distance quantum networks. In contrast, stationary qubits, like those in superconductors, rely on swap gates for communication, increasing gate complexity. Future quantum computers may integrate both types, leveraging mobile qubits for scalable, modular designs, enhancing connectivity and performance. Quantum hardware faces significant challenges. Limited qubit coherence and scalability hinder progress, as maintaining quantum states and reaching thousands of interconnected qubits is complex. Quantum error correction is crucial for reliable calculations, demanding specialized hardware. Cooling and isolation are costly and delicate, while effective integration of qubits, control, and software remains a critical hurdle. Quantum noise and decoherence pose significant challenges in quantum computing. Qubits, highly sensitive to environmental interactions, lose their quantum state, complicating reliable computation. Despite cooling to near absolute zero, global decoherence persists, often due to cosmic rays or radioactivity. These errors remain uncorrectable, raising doubts about achieving quantum supremacy. Quantum error correction, QEC, is crucial for overcoming quantum noise and decoherence, allowing quantum computers to surpass qubit coherence limits. Quantum error correction demands significant computational overhead, with over 99% of operations dedicated to error correction. Techniques like shortcode and surface code are vital, but require low error rates to prevent excessive qubit demands. Achieving quantum advantage demands scaling logical qubits far beyond current capabilities. Fault-tolerant quantum computing requires vast numbers of physical qubits. Simulating molecules like cholesterol needs 1,500 qubits and billions of gates, currently unfeasible. Solving RSA 2048 might need millions of noisy qubits. China's Xiaohong, Origin Wukong, and IBM's Eagle and Osprey processors exemplify progress in qubit scaling. Gate fidelity is crucial for accurate quantum operations, enabling effective error correction. High fidelity ensures algorithm correctness. Gate latency, the time for a quantum operation, must be minimized to perform more operations before decoherence. Balancing coherence time and latency is challenging. Isolating qubits increases coherence but complicates gate interactions, affecting latency. Superconducting computers and ion traps face strict operational requirements. Quantum computers require temperatures near absolute zero to maintain quantum states, posing challenges in cost, volume, and complexity. Conventional circuits overheat at these temperatures, complicating integration. Cryogenic systems are crucial, with companies like Bluefors leading production. China's mass production of dilution refrigerators highlights the importance of supply chain security. Research aims to develop room temperature qubits. Classical control in quantum computing involves issuing instructions, driving gate operations, and error correction. As qubit numbers grow, scheduling and implementing gates efficiently becomes complex. Analog signals, crucial for operations, demand precise timing and fast feedback. Yet current methods lack scalability. Integration challenges include crosstalk and maintaining qubit isolation while enabling strong coupling. Researchers explore three-dimensional layouts and multi-layer integration for scalability. Fabrication is crucial for scaling quantum computers from experiments to commercial production. Thousands of qubits need reliable integration, requiring complex chip designs for mass production. Superconducting computers using Josephson junctions align well with traditional lithographic techniques. While semiconductor and superconductor technologies are compatible, the current demand allows smaller companies to use older fabrication methods cost-effectively. Quantum research is advancing rapidly, with significant developments across the system stack. Notably, quantum volume has steadily increased, reflecting progress. Google's 52-qubit Sycamore chip marked a milestone in 2019, while IBM's superconducting processors have reached 433 qubits with Osprey in 2022, aiming for 1,121 qubits with Condor by 2023. The noisy intermediate-scale quantum, NISQ, era is marked by the potential of quantum machines to surpass classical systems. Experts predict practical quantum computers within 10 to 20 years, with business advantages in 5. Differentiating between proofs of concept and deployed projects is crucial. Full-stack solutions and cloud access are enhancing accessibility and integration in quantum computing. Hybrid quantum classical computing leverages noisy intermediate-scale quantum devices, combining quantum and classical power. Variational quantum algorithms exemplify this, integrating classical optimization with quantum routines. This approach is promising for complex tasks like molecular simulations, enhancing supercomputing clusters' capabilities in simulating molecules and materials, offering a significant leap in computational power and efficiency. Quantum networks leverage entanglement for teleporting quantum states, paving the way for a quantum internet. They offer unbreakable encryption and enable long-distance quantum communication. Distributed computing connects modular units, tolerating noise if units are high quality. Technologies like NV centers and Diamond are key. China's Michius satellite exemplifies progress, achieving entanglement over 1,200 kilometers and quantum key distribution. Quantum computing's potential spans diverse applications. Quantum simulation aids in materials science and drug discovery. Optimization tackles complex problems like logistics. Quantum machine learning enhances artificial intelligence capabilities. Factoring impacts cryptography through Shor's algorithm. Linear systems solve equations efficiently. Quantum sensing offers precise measurements in navigation and medical imaging. The full potential of quantum hardware remains to be discovered. The global race in quantum technologies is intensifying. The United States leads but faces competition, notably from China, which excels in quantum communication and processors. Europe invests heavily in research, yet struggles with practical applications. Russia aims for a 100-qubit computer by 2024, but geopolitical issues may hinder progress. Significant advancements in qubit count and quality are leading to commercially viable quantum machines. However, challenges like quantum noise and decoherence demand intensive error correction and complex control systems. Various qubit technologies offer trade-offs, with research spanning superconducting, trapped ions, and more. Fault-tolerant quantum computers are on the horizon, promising breakthroughs in simulation, optimization, and machine learning. Lowering error rates is crucial for scaling quantum computers, reducing error correction overhead. Scalable architectures must handle noise and complex control while being mass-producible. Algorithms tailored for noisy computers can optimize current devices. International collaboration across physics, engineering, and software is vital. Despite uncertainties, the quantum age is approaching rapidly. Thank you for your attention. As we navigate the complexities of quantum computing, collaboration and innovation will be key. Let's continue to explore and push the boundaries of what's possible in this exciting field. We hope this presentation has provided valuable insights into the topic.